And now we think a little bit more about interpreting velocity graphs and the relationship between velocity and position and displacement. Think of this simple velocity graph here, just a constant positive velocity from some initial time to some later time. And then remember our definition of velocity, it's just displacement divided by the length of time that it takes to make that displacement. And in this case, of course, the velocity is positive. That's just what the graph says. We don't need that twice. But now let's rearrange this equation, the equation that defines velocity or average velocity. Just multiply both sides by delta t, so we have delta t times velocity equals displacement, and velocity is a positive number. The length of time that we have that velocity is obviously a positive number, so displacement comes out positive here. That's exactly what you should expect. When you have positive velocity, that means there is movement in the positive direction. And another way of saying you have movement in the positive direction is that at later times, position is more positive than it was at earlier times, which is just another way of saying displacement is positive, right? The final or later position is more positive than the earlier or initial position. So positive displacement. But now compare this statement here with the graph. Delta t in this case is the same thing as the length of this rectangle, and v is the same thing as the height of this rectangle. And of course, length times height for the rectangle gives us the area of the rectangle. Length, also known as delta t, times height, also known as v, gives us the area of that rectangle. But since length is the same thing as delta t, height is the same thing as v, then L times h is the same as delta t times v, which is displacement. In other words, the area between the velocity line and the time axis is equal to the displacement that happened during this time. And the nice thing about that rule is that it's true for any velocity graph, for any velocity line, no matter how complicated and strange the velocity line might be. In this case, very non-constant velocity, but it is still the case that the area under the velocity line, the area between the velocity line and the time axis, equals the displacement. That's the simple rule if we have positive velocities. If we have negative velocities, there's one little extra complication that we have to take into account. So let's think about negative velocity and think about the simple case, just like we thought about the simple case over there. A constant negative velocity. There's our definition of velocity, but in this case, velocity is negative. So we rewrite that in the same way as before, multiply both sides by delta t, so we have delta t times that velocity, and again that's equal to the displacement. The length of time that we had this velocity is of course a positive number, but the velocity is negative, so the displacement is negative. Anytime you have negative velocity, that means you're moving in the negative direction, which is the same thing as saying the displacement is negative. Later locations are more negative than earlier locations. But similar to what we had over there, the length of this rectangle corresponds to delta t. The length of this rectangle is just t final minus t initial. And then the height of this rectangle is this length here, which is just the absolute value of this negative velocity. So this negative velocity is equal to -1 times the height of this rectangle, -1 times the length of this dimension of the rectangle. So length of the rectangle is the same as delta t, -1 times the height of the rectangle is the same as the negative velocity in this case. So multiplying length times negative height is the same as multiplying delta t times the velocity. Delta t times the velocity is, of course, displacement, which is negative in this case, but delta t times velocity is just the same as multiplying the length of the rectangle times minus the height of the rectangle. But length times height, remember, is the area of the rectangle. So length times height times -1 is the area times -1. Since this multiplication is exactly the same as this multiplication, then this result is exactly the same as this result. And what we have is that anytime velocity is negative, and therefore displacements are negative, then you take the area between the velocity line and the time axis, -1 times that area is equal to the negative displacement. Let's look at a couple examples of that. Here's a graph of velocity versus time. And let's say an object is moving in the positive direction and speeding up. So it gets to a final velocity at some time that we'll call capital T, and then moves at a constant velocity for a little while. Let me make this longer. For a length of time equal to t, t seconds speeding up, and then another t seconds at the constant velocity vf. And so the object was moving, so obviously there's some displacement. We can figure out that displacement by using the area rule. It's a positive velocity, so the area between the velocity line and the time axis is simply equal to the positive displacement. And in this case, the area is the area of a triangle plus the area of this rectangle. So the total displacement between time 0 and time 2t is just equal to this rectangular area, or this triangular area, plus this triangular area is equal to the displacement between 0 and t, and then you add this rectangular area, which is equal to the displacement between t and 2t. So let's do the algebra. This area is a triangular area. Go back to geometry, and the equation for the area of a triangle is 1/2 base times height. So 1/2, and then the base side is just a length of t seconds. And then the height is just vf. And then adding this rectangular area of the rectangle is just length times height, the length, again, is t seconds. And the height, again, is VF. So what we have for the final answer is 3/2 T VF. That's the area. That's the total displacement in this case. Now let's look at a slightly more complicated example. Slightly more complicated because in this case we have some positive velocity followed by some negative velocity. So we start out at some initial velocity and the object moves in a positive direction but slows down to a stop. As the velocity is always positive, but it's decreasing, and eventually it gets to a zero velocity at, let's say, t seconds. And then, after coming to a stop, it turns around and moves in the opposite direction. That is, velocity now has the opposite sign from what it had before, negative velocity. And it starts from zero velocity, but now speeds up in the negative direction, gets stronger and stronger negative velocity as time goes by. And it slows down in exactly the same kind of, or it speeds up now in the negative direction in exactly the same kind of way that it slowed down in the positive direction, so that after another t seconds, the speed is now the same as it was before. It's just that the velocity is in the opposite direction. So a velocity of minus vi is the velocity that the object gets to at a time 2t. Spends t seconds moving in the positive direction and slowing to a stop, and then spends another t seconds moving in the opposite direction but speeding up. So what's the displacement for this whole trip? Well, the total displacement is just the displacement that happened during the first t seconds plus the displacement that happened during the second t seconds. The displacement that happened during the first t seconds is equal to the area of this rectangle, and then the displacement that happened during the second t seconds is a negative displacement because it's negative velocity. So that displacement is equal to minus 1 times the area. The area of this triangle, the triangular region between the velocity line and the time axis. But look at what we have here. Everything is nice and symmetric, and the two areas of those two triangles are equal. The area of this is 1/2 base times height, 1/2, and the base is t seconds, and the height is vi, and then minus 1 times this area, the area of this triangle, is 1/2 base, and this length is again t seconds. 1/2 base times height. Here's the height, which is the height is again vi. Right, the numerical value of velocity at this point is minus vi, but the length of this side of the triangle is a positive number. Length is a positive number always. So in any case, we have equal amounts of area, but traveling in opposite directions. The magnitudes of these two displacements are equal, but they have opposite sign, so those two displacements just cancel each other out. And it turns out that in this case, the object moved through a round trip, moved in the positive direction, then slowed to a stop, then headed in the opposite direction, and ended up right back where it started, because the net displacement for the whole trip was 0. Net displacement being 0 means the final location is just the same as the initial location. So we'll be working with that idea quite a bit. The other idea to introduce at this point is acceleration. Right? We have ways of talking about location. We have ways of talking about change in location, displacement. We have ways to talk about how fast location is changing. We can use either velocity or speed to talk about that. But we also would like to know how fast the velocity is changing, because there are many different situations where velocity will change. Anytime you drop something, for instance, the force of gravity is pulling down on it, so that'll make the thing speed up. Anytime you throw something straight up into the air, the force of gravity is pulling down on it. But if you throw it up, the force of gravity is pulling backwards, so that'll make the thing slow down. There's two simple examples of velocity changing. We want to measure how fast velocity is changing. In other words, we want to find the rate of change of velocity. And the rate of change of velocity is what we call acceleration. And the rule that we use to define acceleration looks very much like the rule for defining velocity. Acceleration is just change in velocity divided by the length of time it took to make that change. In other words, how much velocity change do you get per second? The rate at which velocity is changing. Well, since this rule is so similar to the rule for defining velocity, that means that a lot of the things we said about velocity can also be said about acceleration. For example, let's look at a graph of velocity versus time. And consider just a simple graph, a straight line, and we know how to calculate the slope of a straight line. Pick 2 points on the line, say one point corresponding to some earlier or initial time and another point corresponding to some final or later time. And at the early initial time, the moving thing has some initial velocity. And at the final time, the moving object has a different velocity. And the slope is just the change in the vertical variable, which is velocity in this case, divided by the change in the horizontal variable, which is time in this case. So that change is just the final minus the initial value of velocities divided by the final minus initial times. We can write those final minus initials in a more compact way. Final minus initial velocity is just another name for change in velocity, and final minus initial time is just another name for change in time. So that is the slope on a velocity versus time graph, but that is our definition for acceleration. So in other words, on a graph of velocity versus time, slope is this, which is acceleration. On a graph of velocity versus time, slope equals acceleration. Just like in a graph of position versus time, slope is velocity. On a graph of anything versus time, slope is the rate of change. So in a graph of position versus time, slope is the rate of change of position, which is another name for velocity. And on a graph of velocity versus time, slope is the rate of change of velocity, which is another name for acceleration. Okay. Since acceleration is so similar to velocity, then we can do some of the same things graphically with acceleration that we did with velocity. A velocity versus time graph, slopes are the accelerations. So, for example, here's a graph of velocity, changing velocity versus time. And for a while, the thing is moving in the positive direction and speeding up, and then it maintains a constant velocity for a while, and then continues to move in the positive direction, but slows down to a stop. Continues to have positive velocity, but that positive velocity decreases back to zero velocity. What kind of accelerations do we get in that case? I'll divide it up into 3 different time intervals because there are 3 different slopes in that velocity graph. 3 different slopes means 3 different accelerations because slope is acceleration in a velocity versus time graph. Well, here, during the first time interval, you've got a constant and positive slope, which means constant and positive acceleration. And here you have zero slope, so zero acceleration. During this time, the velocity is not changing, so the rate at which velocity changes is zero. And acceleration is the rate of change in velocity. So unchanging velocity, velocity changing at a rate of zero, zero acceleration, they all mean the same thing. Now in this time interval, the velocity is constant and negative, or the slope is constant and negative. Velocity is positive and decreasing. Slope is constant but negative. So acceleration is constant and negative because on this graph, slope is acceleration. However, this change in velocity happened much quicker than this change in velocity. The amount of velocity change that you get is the same in this time interval and this time interval, but here you get that same amount of velocity change in a much shorter amount of time. The velocity change is more dramatic, quicker, corresponding to a steeper slope. So this negative number must correspond to a faster, stronger acceleration, and the magnitude of this slope is bigger than this slope, or the absolute value of this slope is bigger than this slope. This is steeper than this. So the magnitude or absolute value of this acceleration is bigger than this acceleration. So we would draw that last acceleration in something like that to indicate that the constant negative acceleration here is stronger, greater in magnitude than this acceleration. Okay, and that's those are the basic ideas. We'll add just a few more ideas in the next video, but that's enough to work on for today.